Hey everybody, this is Larry. This is day 26 of the LeetCode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord, let me know what you think. Yeah, I mean, if you're not a new viewer, you know that I usually start with a little bit of just, I don't know, anything really, update about life, I guess. And today I want to, there's a lot of things going on in the world. I want to, uh, what can an idiot like me do, right? In the middle of right now in Medellin, and just being an American and stuff. I don't know, right? But I guess the one thing that I can do is just give a little bit back, and yeah, I'm doing a donation match up to $1,000. I know it's not, a lot or whatever, but it's, it's something. I hope, and yeah, and also want people to kind of hopefully help out. Come to the Discord or my Instagram, send me your receipts, and I'll match some small amount. Every bit helps. Just a couple of bucks, just to show people that we care and support and stuff like that. Yeah, let me know. Come to Discord and just chat about it as well. The world's been crazy, and sometimes you do what you can, right? Anyway, okay. Especially if you enjoy my channel, maybe once or twice, and you find yourself in a maybe fortunate place, fortunate enough to give back a little, just count it as a, I've never asked anyone for money on this channel, and I never will, because I don't know, because my opinion about that is that, I'm a decent software engineer and I can just have a job, right? And if you look up on a lot of different software engineering job websites, or the salary websites, I guess is what I'm trying to say. And if you look through those, you can kind of make good money without convincing people to send you money on the internet, it's a good career. It's a very comfortable career. So I would never ask you money as far as I know. I mean, unless, I don't know. I guess the world is I don't know, things can really go wrong. But, but I do, I hope that you do get into a fortunate place where you can give back whenever you can. And that's always what I ever ask is, two things. One is, just it doesn't have to be a big amount, a dollar or two. I know a lot of my viewers are college students or new grads, or they might be in a country where just like the income is not as lucky as it is in the US or so. And yeah, and the other thing that I always ask is just pay it forward, right? Like if you find it helpful, answer a question that someone may ask in the future, and try to be patient, because that part I'm not 100% either as well, but yeah, right, things, the world's excuse me, yeah, the world's in a crazy place. I hope y'all are doing okay, and I hope that our friends and families in Ukraine, I don't know, right, just make it through it, and yeah. Okay, I know. This is a long thing. I haven't even gotten to the problem yet. Thank you for kind of watching. I don't know. I'm not gonna lie. Sometimes it feels like like what's the point of these stuff, right? So yeah. Okay, so let's actually focus a little bit. Let me try to get back here as well. Yeah, so yeah, follow me on Instagram. I post a little bit of details there, and Discord, which is there's just a lot of smart people there, so also great for helping as well. But yeah, so today's problem is shortest path visiting all nodes. Okay, you have an undirected connected graph of n nodes labeling 0 to n minus 1. You're given an array graph where graphs are by is a list of, okay, so basically you're giving an adjacency list. Okay, return the link of the shortest path that visits every node. You don't have to return the actual path, right? Oh, you may reuse edges. Okay. Oh, okay. This is kind of a silly problem, because initially I was like, okay, well, there are a couple of things, right? there's just knowing the literature. I think that's the tough part about some of these problems, is knowing the literature. And what I mean by that is that if you, and not everyone has the computer science background, and I'm not trying to suggest that per se, because you have to start somewhere, and but that said, knowing the literature means, in this case, what I mean anyway, is knowing what type of problems are NP complete, what type of problems are NP hard, and because as soon as you do that, then you're able to recognize that, okay, there's no optimal solution if in the general case, right? So you could do either one of two things. One is see if there's some weird property of the problem that allows you to be like, okay, I know this is maybe Helm cycle, for example, or something like that, but not this one, but I just mean like looking at another problem, you'd be like, okay, this may be Helm cycle. Oh no, but you can only do this other thing because there's this constraint. So therefore it's not Helm cycle, and I could do it in, not in polynomial time or something like that, right? But that's one. Two is, and then two is that, you just, in real life, what people usually say is either you try to find maybe some sort of randomized algorithm or an approximation algorithm, right? Because it's NP complete or NP hard, depending on what you're doing. That means that you don't have to waste time anymore to figure out a polynomial solution, because none exist unless n equals NP. But yeah, for the purpose of our sanity, let's just say that you're probably not going to find a polynomial one. Though if you do, let me know, and we'll talk it together, and then maybe share that price, and also destroy everything that depends on n equal or not equals NP. Anyway, though, right? So that's a little bit of a calm side joke. Okay, fine, it's not a big deal. But yeah, so this one, I knew that it was going to be one of those hard ones. I actually don't remember. So I accidentally scrolled down, to be honest, and I saw that n is equal to 12, right? And n is equal to 12 is doable for NP complete problems, obviously, because you can just brute force in a smart way, and that's all you're trying to do, I guess, right? But yeah. And yeah, so that's basically the idea. Let's see. Return the link with the shortest path that we should them. No, we start and stop at every no. Okay. So yeah, so I mean, there are a couple of ways to represent the states. That part is, I'm trying to think whether it matters, but basically the states that I would kind of think about is maybe something like this, where, okay, so let's say, let's go to visit. It's a lame name, but basically the current node, right? So let's just say node. Okay, so I just want to make sure that all the numbers are from 1 to 12 or something, right? Graphs of I, that's not, okay, so there's no internal, it's symmetric, and I just want to see where graphs of I is. They don't actually say, maybe they mean it, but it doesn't actually say that graphs of I is, or each node, each element of graph is between 1 to 12, n is between 1 to 12. The length is between 1 to 12, but it doesn't actually say that the inputs themselves. So in theory, if you want to generalize, you could use a key, but I'm just going to assume that this is going to be from 0 to 12 or 1 to 12. So it seems like from 0 to 11, I guess, right? We'll see if that assumption holds. So node will be the current node, which is from 0 to 11, say, right, inclusive. And then we want to do something like a bit mask. Of visited, right? So let's just say visited. So I do have I get a lot of questions about what it is a bit mask. I'll try to do a little bit of a job here, though. I think I'm not going to dwell too much on it. So if there's some confusion here, leave it in the comments or leave it in the Discord, and we'll work through it. But the way that I would think about it is that that I explain always is that a bit mask, it's really not that confusing per se. So let's say we have visited is equal to a Boolean array, right? So that Boolean array is going to have like false, true, false, false, true, true, right? Let's just say there's 6 elements, or yeah, that's 6 elements. And then of course, to write it slightly easier, you could maybe compress it to a string, right? What does it look like as a string? Well, it could look like FT, FFTT, right? And then another way of writing it is, okay, instead of writing f and t's, you could write 0 and 1s, right? So now you have 0, 1, 0, 0, 1, 1. And then another way to say that, of course, is to say, okay, instead of using a string, you just use a number, right? So now this is a binary number, that's this. And then another way that you could say is that, okay, now we have a binary number. What is this as a number, right? I have to do the math this one though. This is 1 plus 2, so that's 3, 4, 8, 16, so 19, right? So that's basically what a bit mask is, right? So that is basically there's some Boolean array that you convert to a number. And that's basically how you do it. And then there are a couple of operations. I'll show it when it comes up, but that's basically the idea. For this problem, I'm not going. Because I actually do want to get somewhere today or tonight. So I will use this thing that is in Python called cache, but we will still go over the complexity. So you cannot use it. Or one thing that I always tell people is that you should not use it unless you really understand how complexity works with dynamic programming and memorization. I mean, you can, obviously, I'm not going to police you, but you shouldn't, because that's when you run into trouble. When you ask, but I add cache, why is this still TLE? I'm like, well, because you don't really understand it, right? Okay, so then let's go over the end states, right? So what do we want the end state to be, right? Well, if visited is equal to true, then we end, right? So that basically, if visited is equal to, so and this of course equals to 1, 1, 1, 1, 1, and 1, which is equal to 1 times n, kind of roughly speaking. I mean, obviously this is not the notation, but I'm just using rough. And of course this is if you look at this number, and you may see this sometimes, right? It's going to be something like this, right? -1. So if you see this in other people's code, that's basically the logic and basically the reason, right? It's just basically this n plus 1 minus 1, right? So yeah, so and this is equal to 1 shifted n times to the left. So yeah, so that's basically, if this is equal to minus 1, then this is good, right? So we return 0 because we visited every node. That's basically the idea. Let me think about this for a second. I want to make sure that I'm a little bit careful. Because I think you can do it in a way such that you can have infinite looping back and forth. There are ways you can make it so that doesn't happen or harder to happen. But for now, I am going to do it in another way, which is, because basically you can just look at all the intermediate neighbors, right? You could be like, okay, 1 is neighbors, or in this case, example 1 is connected to, let's see, 1 is connected to, 0 is connected to 1, 2, 3. So you could be like, okay, with 0, let's go 1, 2, and 3, and then 0 could go to 2, 2 can go 0, and then 0 could go to, and then that's where you get an infinite loop, right? But another way of writing it is that you can only go to an unvisited node with an undetermined distance. What I mean by that is that, let's say you start at 0, you go to 2, and then from 2 you want to go to 1 or 3 because you already visited 0, right? Of course, 2 going to 1, I'm looking here again, 2 going to 1 will have an edge weight of 2, right? So that's basically the idea, is that generating an alternate graph where that's the case. And of course, that's not that hard per se, we just have to do it. And I'm going to try to, okay, so let's put this ahead a little bit, and then we'll use Freud-Warsaw's algorithm. There are other ways to do it, of course, but I'm a big fan of Freud's, so let's go. So distance is equal to, let's just say infinity times n for, right? So now we have an n by n distance matrix, right? And it's infinity. So of course, the first thing you write, then now we pause to input graph. So now for edges in graph, let's enumerate this as well. What did I press? So yeah, so for node I, so then now we go distance of I of, well, that's actually, oops. For edge in edges, distance of I of edge is equal to 1, right? So that sets it up. I think we should also do, I don't think this matters, maybe not for this one anyway, but it's just the convention that I'm usually doing, unless this is a compelling reason why that's not the case, right? So that's basically Yeah, that's basically what I'm going to do here. Yep. And then now this allows us to go from, okay, let's say for I in range of n, right? And then we ask ourselves, okay, if visited of I, of course, that's not the notation because as we said, there might be actually, no, that's good, I think. So if visited was a Boolean array, that's what we would do, right? If this is not visited, whoops. So if this is not visited, we go visited, right? So we visited, dot, 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 right? So that's basically what we do. But of course, we're doing with a bit mask. And a bit mask, as we said, it's going to be like, some number 10, something like that, right? And then the idea here is checking whether the ith bit is a 1. So the way that we do that is just take a number that's left shifted by I, and then see if that's a 1, right? And that's basically the idea behind this bit mask, is if, let's see, 1 shifted by I, if we end this with the visited, right? If we end this and is equal to 0, that means that this is not visited. Because if you end these two numbers, for example, oops, it'll be non-zero, it'll be 1 shifted, whatever. But if you had shifted here, then this would just be a 0, right? So then that's why this is checking to see if it's unvisited. There are, of course, other ways to write it, but that's the way that I'm explaining it and writing it. So, yeah. Because, but all of them have the same logic. It's just different, different way of writing it, right? So, yeah. Okay. So then now, if that's not the case, then I have to set a best is equal to infinity. I didn't set infinity actually, so that's just a big number. It doesn't really matter, because this is connected. So you always get an answer that's like, I don't know, what is the worst case answer? Like n times 2 maybe, something like that. If you visited every edge twice maybe. I don't know if that's true, but either way, if you choose a big enough number, it should be okay. Okay, so if that's not the case, then best is equal to min of best. We visit this node I, we toggle this node I, and then we add that by the distance. So now this is the distance from node to I, right? Hopefully that makes sense. I think the only part that's confusing, especially if you haven't done bitmask, is this one. But basically, this is same thing as here, right? So we know that this overlap is 0. So that means that if you add those two together, then this 1 will make this a 1. And when you do the recursion, right? So that's basically the idea. And of course, the cost of that node is all this stuff plus the distance. And then at the very end, we just return best. Of course, this is not memorized, but let's take a look. But of course, and also this is assuming that some stuff which we have to go, right? So then now outside we start again because we want to be able to start from every node to see what's best. So we should do that. So for I is range of n, let's say we visit I and then visit it, right? I guess technically you got to kick off like -1 or something weird, but this is probably a little bit cleaner. And that should be good even if it's a little bit slow. Let's actually run the test cases to see if we at least have the right answer. We might time out. Oh, did I have a typo somewhere? Oh, this is not visited. Oh yeah, because that should be just 0. So you should kick it off with 1 node being visited. Okay, so we're wrong here. That's a little bit awkward. Maybe I did something weird. I have to update this though, actually. I'm dumb. Sorry, friends. What I forgot to do is, I constructed this, but then I talked about it, but I forgot to actually code it, which is the Floyd-Warshall part, right? So that's what we're gonna do. So here we go for k in range of n, for I in range of n, for j in range of n, distance of ij. Did I mix this up? No, I think this is okay. Equals min of this ij, or this of ik plus, and this is just Floyd-Warshall, right? Let me write it up so you could Google if you like. Okay, now hopefully this should be good. And that makes sense because it would run out of loops anyway. Okay, so this is right, but obviously too slow. So the thing we want to do is memorize this. I'm a little bit lazy on this one today, to be honest. Hopefully, this is already good enough explanation. So, but I will analyze it to know that this is fast enough. Of course, if you had if you're doing it for a contest or even an interview, you would analyze it first. Otherwise, you wouldn't implement something too slow. But in this case, node is from 1 to 12 or 0 to 11, I guess actually. But this is 12 or O of n. And then visit it. As you know, this can be for every I bit, it has could be 0 or 1. So this is actually O of 2 to the n or 2 to the 12 in the worst case. So that's the number of possible inputs, right? For each input, so yeah, let me write that first. So possible input is equal to O of n times 2 to the n. And then now each input takes, each input will do an n loop. So that means that each input will take O of n time. So then possible time, total time is O of n squared times 2 to the n. And of course, and of course, possible total space is O of n times 2 to the n, because, no, this is time, O of one space, right? Because we just store it away. And that's basically what cache does, kind of. Let's just say it does. And yeah, and of course, this is also linear, but each core is going to be O of 1, so this is just linear, and that's why we don't mention it. Here, then, let's give you some, one the code real quick. It looks okay. Let's give it submit, and hopefully that's okay, and we don't have any typos or silliness. If it is, that's fine too, we can fix. Oh, I didn't C++ last time. That's interesting. Yeah, so we did finish it. Yay! We did bitmask dynamic programming. Hopefully this is a good one. It's a 697-day streak. That's good too. That's all I have for this one. Yeah, we already did the complexity. Curious what I did last time. Did I do it recursively? I did do it recursively, okay. I did do the Floyd-Warshall algorithm as well, so yeah. Okay, cool. I don't think I have anything else to say about this one, so I urge you to, take care of yourself, take care of others if you have the opportunity to. Stay good, stay healthy, to good mental health, and yeah, good luck to all our Ukrainian friends and family. Anyway, see ya.